In this session, we consider the hypergeometric random variable, and we will build it up from an example, and we'll generalize the example as we go along. So let's say I have 7 cards. I deal 7 cards from a fair deck of 52. So how many 7-card hands are there? Okay, we've done this a number of times. Right, to construct a hand, well, out of 52 cards, you choose 7. The cardinality of the sample space is 52, choose 7. There are 52, choose 7, 7-card hands. Okay, what's the probability of this exact hand? 4 of clubs, 4 of diamonds, 4 of hearts, 4 of spades, 3 of spades, 2 of spades, and ace of spades. Well, let's H be the event that you get exactly that card. All 7-card hands are equally likely. So by the work we've done before, it's the cardinality of H divided by the cardinality of S. It's 1 over 52, choose 7. Right? There's only one hand, 7-card hand, that meets all those requirements. Okay. Let's generalize a bit. How many 7-card hands have exactly 1 queen? Okay, so how do we, well, there are 52, choose 7-card hands, we know that. How many 7-card hands have exactly 1 queen? Well, out of 4 queens, we need to choose 1. So let's think about this process. We'll do it this way. We're going to select 1 queen out of 4. And then out of the 48 cards that are left over, which are not queens, we need to choose 6. So we've chosen 1 plus 6. It's 7 cards. And we have taken exactly 1 queen. So the number of such hands is 4. Out of 4 queens, choose 1. And out of 48 non-queens, choose 6 to make a total of 7. A 7-card hand. And then, so that's the cardinality of the event A, which is getting a 7-card hand with exactly 1 queen. And so what's the probability of getting a 7-card hand from a fair deck with exactly 1 queen? It's this number here divided by 52, choose 7. Okay. Now let's generalize a little bit. How many n-card hands are there from a fair 52-card deck? How many n-card hands are there? Well, how do you construct an n-card hand? You pick n cards randomly from 52 without replacement. And the order within a hand is not important, and the order within the remaining cards is not important. So that would be that. How many card hands are there? There are 52. Choose n card hands. Okay. Now, how many n card hands have exactly 2 queens? Let's think about how we would construct this. There are 4 queens. We have to choose 2. And then out of the 48 remaining cards, non-queen cards, we have to choose n minus 2 to make up a total of n cards in our hand, 2 of them being queens. So the number of such hands is from 4 queens, choose 2, and from 48 cards, 52 minus 4 cards, non-queen cards, choose n minus 2 to come up with a total of small n cards, 2 of them being queens. Okay, and again, how many n card hands from a fair 52 card deck? 52 choose n. So what's the probability that in an n card hand you have exactly 2 queens? It's 4 choose 2 times 52 minus 4 choose n minus 2 divided by 52 choose n. We're using the equally likely idea that all of the n card hands are equally likely coming from a fair deck. There's no cheating going on. Okay. How many n card hands have exactly x queens? So x could be 0, 1, 2, 3, and 4. Well, out of 4 queens, we have to choose x queens. And then out of, well, there were 52 minus x sorry. There, we now have to choose the non-queen cards, right? So that would be 52 minus 4. And then we've chosen x queens, so now we have to choose n minus x other cards to make an n card hand. So 4 choose x times 52 minus 4 over n minus, to choose n minus x. Okay, so then the probability is the cardinality of the event of getting x queens divided by the cardinality of the sample space using the equally likely idea. So then we have 4 choose x times 52 minus 4 choose n minus x divided by 52 choose n. Okay. Now, instead of here, in this case, we have 52 distinct symbols, right? There are 52 distinct cards in a deck. Well, what if instead of 52, we had n symbols, n unique symbols, capital N unique symbols? So let's say there are capital N distinct symbols. We're going to select n of them, and within that order, none. And let's say that within that select, once you've made the selection within those, the ordering of those small n symbols doesn't matter. And the ordering within the n minus n symbols does not matter. Okay, so then there are n choose n ways of doing that. Capital N choose small n ways. So supposing that k of the small k of the n symbols of a particular type. So how many ways are there to select k of them if the order within the selection does not select x of them if the order within the selection does not matter? Well, there are k symbols of a particular type of which you are to select x with order not mattering. So there'd be k choose x of them. And then there are n minus k symbols, which are not of that type, right? And if you want a total of small n symbols, then that would mean that you have to pick n minus k of those. Okay, so out of the k symbols that were a particular type, you have to choose x. Then there are n minus k symbols which are not of that type. And out of those, you have to choose n minus x to make up a total of small n choices. So it's k choose x times n, capital N minus k choose small n minus x. Is it doing that? Now, if the selection was fair, and all such, that would mean that all such selections of small n symbols is fair is equally likely. And then the probability looks like small k choose x times capital N minus k over small choose n minus x divided by capital N choose small n. Okay, so basically as we've generalized along the way, we get to this probability, and that is our that's basically how we're defining the hypergeometric random variable. Okay, so there are small n items selected without replacement from n total items. K of the items can be called successes, n minus k can be called failures. And capital X, the hypergeometric random variable, is the number of successes of a hypergeometric experiment. So the probability mass function for that, so the probability that capital X equals small x, given that you have capital N total symbols, you're going to pick n of them, and k of them are of a particular type called the success. And you want the probability of x successes. That's given by k choose x, capital N minus k divided by small n. Choose small n minus k minus x divided by n choose n. That's the hypergeometric. That's the probability mass function for the hypergeometric random variable. Okay, so if you do the calculations, well, what would that be? That would be the summation. The expectation would be the summation over all allowed values of x. So I guess those could go from 0, 1, 2, 3, all the way up to small k, x times f sub x. If you do that calculation, you get small n times k over capital N. And if you do the calculation for the variance is equal to the variance for the hypergeometric random variable is capital N minus small n over small n minus 1 times small n times k over capital N times 1 minus k over capital N. Okay, for very small samples, sorry, not the opposite of very small, for very large samples, the hypergeometric distribution can be approximated by a binomial. So if n is equal to 3 times 10 to the 26, you may as well just be using the binomial distribution rather than the hypergeometric. Okay. I'll let you think about what that is, why that is. You want to think about how these terms are changing, or how different they get when you've got a very large capital N. Okay, so if n is small compared to capital N, say small n divided by large n is less than or equal to 0.05, we can approximate using the hypergeometric by using the binomial distribution. So that is, if you've and then this k over capital N in the hypergeometric distribution is that would be the p in when you're approximating using the binomial distribution. Okay, so you could have a situation in which your you know that you should be using the hypergeometric distribution. Okay, but your capital N is very large, and your small n is very small compared to that. And then you can get a reasonable approximation by using the binomial distribution. Okay, so let's do a problem. Okay, so we manufacture widgets. We're supposed to send 10,000 widgets. Okay, so in the process of manufacturing the widgets, we set aside 100 that were defective, but we shipped them by mistake. Okay, so one choice is to tell Hypermart we're just going to recall the shipment because we sent you some defective widgets by mistake. We're sending you another batch. Well, on the other hand, 100 widgets out of 10,000, and they're mixed in together, right? We think the customers buy about 10 widgets at a time. So maybe the customer won't be complaining. I mean, if a customer were to buy 10 widgets and 10 of them were defective, then there would be complaints, and then Hypermart would get back to us and complain. But, 10,000 widgets are being sold. Some guy gets one widget that's defective out of 10, maybe. Once in a while that happens. Yeah, maybe we can get away with it. Maybe Hypermart won't notice. Okay. So the ethical answer is, of course, that we should tell Hypermart that we've accidentally sent them 100 bad widgets. Okay. All right, let's say we're not ethical. Let's say we don't tell Hypermart. What is the probability of some unfortunate customer, or some fortunate customer, choosing 10 non-defective widgets? Okay. Well, if we estimate using the binomial distribution, then n over p, small n over capital N. Small n would be the 100 defective widgets, right? Here, success is finding a defective widget, right? It's 100 divided by 1,000 is 1%. Now, as the defective widgets are bought up, this probability would change, right? We're just going to keep it constant and treat it as if we're doing a binomial distribution. Okay, it actually changes the approximation. The binomial approximation to the hypergeometric distribution is that p is a constant. Okay, so the probability of someone choosing 10 non-defective digits is like 90.4%. Okay. All right. So next example. We have a factory, let's say, that produces widgets. It produces widgets in lots of 45. Testing a widget destroys it. So we want good quality control. We can't actually test all the widgets, right? So let's think about that. How about this strategy? We could come up with all sorts of strategies. What we could do is we say, all right, you produce a lot of 45 widgets. I'm going to test 5 of the widgets. We're going to ship the lot if and I'm going to be destroying the widget when I test it. So we shipped a lot if we don't detect any defective widgets. Okay, and we don't ship the lot if any defective widget is found. Okay, so if there are no defective widgets in a lot, what is the probability that we ship the lot? Okay, given that there are no defective widgets in a lot of 45 widgets, what's the probability that we ship the lot? And given this policy, well, we have 45 widgets, none of them are defective. We take 5 of them and we destroy them in the testing, and we don't find any defective widgets. Okay. So if there were no defective widgets in the loss, then this policy would work and we would ship the lot. Okay. So the probability is 1. And that works. That's fine for us. What if there is one defective widget? There's one defective widget. What's the probability that it is not detected? Okay, so there was one defective widget in the lot. We select 5 widgets for testing. And if the widget, okay, if the widget was picked up for testing, if it was selected for testing, we would realize that it was that there was at least one defective widget in the lot, and we would not ship. And if it was not detected, then we would we would ship. Okay. Okay. So how do we choose all 5 widgets from the 44 that are not defective? Okay, so the one out of the one, so we have 1 which is defective, and we have 44 which are not defective, right? So in order to get no defective widgets in the 5 widgets that we're selecting, out of that 1 defective one, we have to choose 0. Out of 44 perfectly good widgets, we have to choose 5. Okay, so that's the number of ways of not selecting the defective widget. And there are 45 choose 5 ways of selecting 5 widgets. So the probability of not selecting that is 1 choose 0 times 44 choose 5 divided by 45 choose 5. That's equal to 8/9, 0.8 repeating. Okay. So this policy of testing 5 widgets out of 45 is, if there's 1 defective widget, there's an 88% chance, 89% chance that we're going to ship. And so we probably shouldn't be giving a guarantee that all widgets are defect free. Okay. What if there are 2 defective? What is the probability that they are not detected? Okay, so we have to separate things into, we have to select 5 widgets, and we have to miss 2 of the defective ones. So we have to, out of the 2 defective widgets, we have to choose 0. Out of the 43 non-defective widgets, we choose 5, right? There are 45 choose 5 ways of choosing the widgets. That gives us 26 out of 3, which is like 78%, 78, 79%. Okay, so the customer has a better than 50% chance of getting 2 defective widgets with this policy. All right? We had 45, we tested 5, so we're shipping 40, and there's a 79% chance that 2 defective widgets are going to be sent with those 40. Okay. What if there are 3 defective? What's the probability that they're not detected? Okay, so there are 3 out of 3 widgets we have to select 0. 3 defective widgets we select 0. Out of 42 remaining, we select 5. And there are 45 choose 5 ways of selecting 5 widgets. And that gives us approximately 70%. So if we have 3 defective widgets, there's still a 70% chance that we're going to ship those 3 in a shipment of 40. Okay. What about 5 defective? Okay. And what's the probability that we're going to ship? Well, we have to choose 5 out of the 5 defective, we have to choose none. Out of 40 non-defective, we have to choose 5. And there are 45 choose 5 ways of selecting 5 widgets from 45. And that's still over 50%. So if we have 5 defective widgets out of 45, we could miss those 5 defective widgets with a 54% chance. And out of the 40 that get shipped, right, 5 are destroyed. Out of the 40 that get shipped, 5 of them are going to be defective. Okay. All right, so this doesn't seem like a winning strategy. Okay, so that's our introduction to the hypergeometric random variable.